In the previous lecture, we discussed about, it was super interesting. We discussed about the derivatives of many functions, like trigonometric functions and the exponential functions. Could you please remind me what is the derivative of the exponential function? Like, what is the derivative of the e to the power of x? It is simply e to the power of x, right? We also introduced this notation of the derivatives, right? So which basically is coming from the definition. If you remember, the definition of the derivative of the function at some point x0 is equal to, so little change of the function, right? The function's value, which is f of x0 plus the h minus f of x0, divided to the little change on the x. It was like x0 plus the h minus x0. Okay? And when the limit goes to the, so when the h goes to the 0, then this is going to be exactly the derivative. And this notation actually explains this. Just change the function e to the power of x and just divide it to the little change in the x. So this is different notation. And the cool thing about this notation is it is going to tell us the variable of the differentiation. So it appears it is very important for us to know which variable of the differentiation which we are using. So if I tell you what is the derivative of the e to the power of x with respect to the x, you can tell me that this is equal to the e to the power of x. Or for example, what is the derivative of the x in a square with respect to the x? It is going to be equal to the 2x. But if I say what is the derivative of the x in a square with respect to the y, what is this? So if I say that it doesn't depend, yes. Okay, but what if they are independent? For example, let's say if you change the velocity over some time, right? What is this, by the way? Okay, if you change the distance over the time, so you measure the distance in 5 seconds, how much distance you passed, right? Can you close the door? You pass the 5 meters in 1 second, right? So if you just divide the change in distance to the change in time, it is going to give you what? The velocity. Okay. So you basically know how the velocity is. What is the velocity, right? By just knowing how the distance is changing over the time. Okay. So if I say here, I mean how fast the distance is changing. So the meaning of the velocity is how fast the distance is changing, right? So if I just measure the change of a distance, okay, then I also measure the change. What is it? Huh? No. If I measure the change in the distance, and if I measure the temperature, and if I say, hey, how fast the distance is changing? Hmm? Oh, it's a bad example. Uh, so let's figure out another example. So what do you think? Is it your grade from Calculus 1 somehow depends to your grade in Calculus 2? Yes? Okay. So I can take the derivative, for example, of Calculus 2 with respect to the Calculus 1, for example. Okay, I can say, hey, what is going to be the grade for Calculus 2 if your grade from Calculus 1 is A+, for example, okay? There are two dependent things. But at the same time, I can tell you what is going to be your grade in Calculus 2 if you've got A+ in philosophy. What is this? Well, I mean, these two events are independent, right? It doesn't matter what you've got in philosophy, your grade in Calculus 2 is not going to be changed, okay? The same is here. So if I say here, how much the x squared is changing if I change the y, and if these two variables are not dependent, you basically say it is not changing. It doesn't matter how much you change the y, x squared is not going to be changed, okay? It is going to be simply equal to the 0. So do you remember that if you have a constant, right? So for example, derivative of a constant with respect to the variable is equal to the 0. And I hope that you know this, and we can even prove this. The meaning is that, so it doesn't matter how much you're changing the x, the 2 is going to be there, right? So let's catch this function. So what is the function of the 2? Do you remember? Y is equal to the 2. It is going to be simply the vertical line, right? Yes? Are you sure? No, horizontal line. Okay. So y is equal to the 2 is going to be the horizontal line which is passing through here. Okay? And I'm saying, hey, just choose this x, this point, okay? Then just choose the point which is nearby, and then divide the change of the height to the change in the width. It is simply 0 because it is not changing. It doesn't matter how much you're changing the x, right? So the y is not changing. So that is why its derivative is going to be equal to the 0. So the variable of the differentiation is very important. If you are taking so sometimes you can get the derivative to be equal to the 0, not only from the constant, but from the functions as well. If your variables are not dependent, then their derivatives is equal to the 0, just because of this logic again. So it doesn't matter how you're changing one variable, the second is not changing because they are independent, okay? It doesn't matter what you've got from philosophy. If you increase your grade from philosophy from B to the A+, it doesn't depend on the calculus. Your grade from the calculus is going to be the same, right? Do you understand this? So this is what does it mean, the variable of differentiation. It is superbly important to know what is the variable of the differentiation. And this notation is going to tell you what is the variable of differentiation. If I say, for example, what is the derivative of sine of x with respect to the x, you tell me what? Cosine of x. And if I say, what is the derivative of the sine of y with respect to the y, what you say? Cosine of y, okay? If I say, what is the derivative of the sine of y with respect to the x, you say is 0, if they are independent, okay? So, and if I say, what is the derivative of the sine of x squared with respect to the x squared? Cosine of x squared, right? So here you see, so you just need to look to this x, y, or x squares as just the symbols, okay? So the x squared here is the same symbol as the x in our previous example, okay? And this is not a function of the x. It is not an x squared anymore. It is going to be looked to simply the symbol. So I just gave you these examples because last time at the end of the lecture we discussed something which is called the chain rule. The necessity of the chain rule is that, so sometimes you need to give, so you see, so if this variable which is inside your function, so do you remember how we call the variable which is inside a function? So you should know this from programming, right? So how do you call the variables which you're describing in your function? Arguments, right? Argument, right? So the variable, yes? Yeah, okay. What is an argument? What is an argument? Okay, so the variable of the function, right? You see, so if the argument of the function is the same as the variable of the differentiation, right? It's the same as the variable of the differentiation, then I can make this, okay? If they are different, then it is difficult, okay? So the thing is, so sometimes we have to take the derivative of such a functions like sine of x squared with respect to the x. Okay? So sometimes we have to take the derivatives of the composite functions. So do you remember what we call the composite function? What is the composite function? Yes? Composite functions are the functions which are obtained by composing two functions, right? Inside the another one, right? Okay. Yes. So here, which two functions are composed? Sine of x and x squared, right? If you take sine of x from the x squared, you're going to have sine of x squared, okay? So sometimes we need to take the derivatives of the composite functions. I'm pretty sure that most of you know how to take the derivative of the sine of x squared, right? It is going to be cosine of x squared times the 2x, okay? But I would like to look to this problem from the perspective of this notation. So here I've got this notation, d of sine of x squared over dx. And we've agreed algorithmically that I can make this if and only if the variable, the argument of the function is going to be the same as the variable of the differentiation. And if they are not the same, then what we have to do? Yeah. If they're not the same, what we have to do? So you see, are they the same? So one is x squared, one is x. They're not the same, right? Huh? Yeah, if the argument is not the same as a variable, then we have to what? Huh? Okay. Yes, exactly. Do you remember our favorite phrase that we are engineers, that we can always find a solution, right? And if something doesn't work, we are going to force this to make this to be worked, right? So it is essentially, if they're not the same, we are going to force them to be the same. And the logic is going to be like this. So it is equal to derivative of the sine of x in a square divided to the dx in a square. Okay? I'm going to make it the same. So in this case, now I can take the derivative, right? So since the argument of the function is the same as the variable of the differentiation, then its derivative is going to be equal to the cosine of x in the square. But the problem is they are not the same, right? I made the variables all the same, but this equality on the left hand side, right? On the left hand side is not the same with the one which is on the right hand side. Okay? So in order to make them equal, I'm going to multiply this to the additional term. I'm going to multiply this as a dx in the square over dx. Okay? So now they are the same, right? So the equalities, the left-hand side is the same as the right-hand side because you can cancel this dx squares, right? And it is going to be the same. And even more, I can take the derivative of every term, of the white term and of this strange color term. Okay? So what is the derivative of the sine of x in a square? With respect to the x in a square, right? Not with respect to the x. With respect to the x in a square, it is going to be cosine of x in a square because you need to look to this as the symbol. This is symbol, this is symbol, this is the same symbol. And it is multiplied to the derivative of the x in a square with respect to the x, which is 2x. Okay? So this rule we call as the chain rule. Okay? Because this is kind of connected as the chain. So we can make this with the composition of the three functions. For example, if I gave you like e in the power of sine of x in the square. Okay? So if I say, could you please take the derivative of this one with respect to the x, then you have to make this trick 3 times. Okay? So can we make the derivative with respect to the x? No, right? What is the argument of the function, by the way? So what is an outer function? The most outer function is e, right? E of something. So you need to just like close your eyes. Okay? You need to see this. E is something. Okay? It doesn't matter what is this there. But you have to divide this to the same thing. Okay? So it should be divided to the same thing as the power of the e. So as the argument of the e. So it is going to be equal to d of e of sine of x in a square over d sine of x in a square, right? I'm going to force this to be the same as the argument of the function. But since I have to do this, I'm going to multiply this because I need to keep the balance always, right? I have to multiply this to say d sine of x in a square over dx. In this case, they are the same. But again, the problem is I can't really take the derivative of the second function because this is x square on the argument, and this is x on the variable of the differentiation. I'm going to make this x in a square. So that is why I have to multiply this to the dx square over dx. Okay? So, and again, so all of these things are kind of connected as the chains. Okay? So this is why this rule is called the chain rule. It is connected as the chains. Okay? So in this case, I can make the derivative, right? You see, so all the requirements are fulfilled, right? So it is like always, like if something works, then you can do this, right? If the argument of your function is the same as the variable of the differentiation, then you can work. Then you can take the derivative. If not, just then make it. Okay? And this is the trick how you're going to make this. Then let's take the derivative. What is the e power of something over something? e power of something, right? Okay. Derivative of, oops, something's changed. It is going to be e in the power of sine of x in a square times t. So cosine of x in a square times t, 2x. Okay? Cool. So this is what is called the chain rule. So we are going to do a couple of exercises. So let's do one more example. Let's say f of x is given as the square root of x squared plus 1. What is the derivative of this function? What is the derivative of the f of x with respect to the x? Okay? Then I'm going to write this again. So let's do this together. So d of square root of x squared plus 1 over d. So what I have to do here so that I can make this derivative, I can take this. Yes? You finished? Okay. X squared plus 1? Okay, so what I have to do this, what should be the variable of differentiation? Can you help me, please? X squared plus 1, right? Because we know how to take the derivative of square root of something, okay? Now you need to look to this x as something, okay, always. It is not simply like x, but it can be anything there. Square root of y or square root of x squared, it doesn't matter. Square root of, I don't know. Square root of divided log. What is the derivative of the square root of divided log with respect to divided log? By the way, 1 over 2 square root of divided log, right? It doesn't matter what is there under the square root, okay? So, I'm going to change this to something. Derivative of the square root of something with respect to something times the derivative of the same thing over dx. Then this is going to be 1 divided to the 2 square root of x squared plus 1 times to the 2x. Okay? Cool. So you have to make a couple of exercises before coming to the next lecture on this topic. Today we're going to discuss about something which is called like implicit differentiation. Implicit differentiation. Do you understand the meaning of the implicit and explicit? What does it mean explicit and what does it mean implicit? Explicit. Huh? Yeah. So explicit means that your function or your terms or something is described like as it is, and implicit is we know that it happens there inside, right? It is hidden, right? I can explain you this, for example. I can say that, hey, so I'm going to give you the online quizzes. If you want, you can make them. If you don't want, you don't make them. It is not mandatory. Okay? For example, I'm going to give you every week the online quizzes. And you go to the classroom. For example, that's a okay? Hypothetically. Okay? And then I'm going to say they're not mandatory. Would you do them? Probably not, right? And if I say, hey, so your questions in the exam are going to be taken from the online quizzes. Okay? So the online quizzes are not marked, right? So they are not going to affect your grade explicitly. They are going to affect your grade implicitly, right? So if you do the online quizzes, you're going to write the exam better, so that is why your grade is going to be higher, right? You see, so this is what is called implicit. So there is something there, so you know that it exists, but it is not expressed explicitly. Okay? So if something is not expressed explicitly, we say that this is expressed implicitly. Okay? Does it help you to define the implicit? So, if not, I'm going to explain you this in this way. So explicit functions is going to be y is equal to the f of x, okay? Where on the left hand side you simply have y, on the right hand side you're going to have all of the terms with the x. On the right hand side you don't have anything which is connected with the y, okay? For example, y is equal to x in the square, y is equal to the sine of x in the square, or y is equal to the e to the power of sine of x in the square, right? So you see, so in all of these examples, on the left-hand side, you've got just y. On the right-hand side, everything is the x. Sometimes it is not possible to do this. Okay? For example, if you are given like some complicated function, like a sine of like square root of xy plus the y in the square is equal to the 3. Okay? This is implicit function. So there is a dependency between x and y. And I can express the dependency using this equation. But I don't know what is the dependency between x and y explicitly. You know what I mean? So x and y are dependent, but I don't know what is this. I don't know what is y is equal to f of x. But still, I would like to find y prime, as I wanted to find y prime before. Okay? And we are going to learn how to do this. So this is called the implicit differentiation. So here, if you are given simply y is equal to the sine of x in a square, you know what is the y prime? It is cosine of x in a square times to the 2x. Well, I would like to know what is the y prime here. Okay, so again, so you still understand what is the y prime? Y prime is derivative of the y with respect to the x. It's like how much the y is changing if you change the x. Okay? So let's start from the easier example, because honestly I don't know how to do this for this one. I just wanted to give you an example of an implicit function. Okay? So implicit, the relationship between x and y. Okay, so let's start with the equation of a circle. X squared, y squared is equal to z 4. I would like to find a y prime. Okay? So previously we learned that the derivative of the y squared with respect to x simply equals to 0, because we say that the y and x are independent. Now I'm saying that they are dependent. Y is some function of the x. It means that y depends on the x. If I change the value of the x, y is also going to change, right? Because, for example, if you find yourself on a circle, do you remember that this is a circle, right? This is the circle. What is the radius of the circle? 2. What is the center of the circle? 0, 0, right? So this is the circle with the center at the point 0 and 0, and with the radius 2. 2. Right? Okay. If you find yourself in the circle, and if I'm going to move horizontally, you're obviously going to move vertically as well, right? Otherwise, you're going to be out of it, right? So should I do this? I can make beautiful circles. So let's say you are going to find yourself here. Okay, you are on the circle. You can't be just go out from the circle. If you're going to move now horizontally, obviously you're going to move vertically as well. Okay, y depends on the x. I would like to know how much the y is going to change if I change the x. I would like to know what is the y prime. Okay, so in this case, I'm going to take the derivative and find the y prime, and this is going to be super easy. Okay, so let's do this together. So do you know what is the derivative of the x in the square with respect to the x? Yes? 2x, okay. What is the derivative of the y in the square with respect to the x? It is not 0 anymore. Because previously I told you that, hey, they are independent, okay. So that is why it is 0. Now they are dependent. Y is some function. Y can be sine of x, for example, or cosine of x in the cube. I don't know what is the y, but definitely it depends on x. Okay? Yes? Okay, let's do this using the chain rule. Okay? So do you remember, in order to take the derivative, what I have to do is I need to make this 2y in the square times as a dy. Okay, so over dy times as a dy over dx. Right? And I hope that you understand why we're doing it, right? Because I have to make the same variables here, right? And I have to multiply this as a dy over dx in order to keep the dx, right? So what is the dy squared over dy? 2y, right? It is equal to the 2y. So it is simply the derivative of the y squared with respect to the y, okay? But I have to additionally multiply this as a y prime because the definition of the y prime is dy over dx, okay? Y prime is the derivative of the y with respect to the x, right? So this is dy over dx. Do you remember the first equation which we wrote for today? We started with this. So the y prime is dy over dx, or f prime is df over dx. Okay? So the derivative of the y squared is going to be 2y times the y prime. And I'm going to just plug this into this equation. So I'm going to have this equation, x squared plus y squared is equal to the 4, and I'm going to take the derivative with respect to the x. It means that I'm going to take the derivative of every single term separately, okay? Derivative of the x squared is going to be equal to the 2x, derivative of the y squared is going to be 2y times the y prime, and derivative of the 4 is going to be equal to the 0, because it is a constant, it is not depending on the x, definitely, okay? Then I'm going to find the y prime from here, it is going to be equal to the minus x over y. Okay. This is how we are going to find the derivatives of the y, so essentially y prime. And this is what is called implicit differentiation. We're finding y prime from the implicit equations. Okay? So it is very useful. For example, do you know what's the derivative of the x cubed? Oh, do you want an interesting example? So let's do one boring example, then we'll come back to the interesting ones. If I say you, let's do an example. So you're given an equation x cubed plus y cubed is equal to the 6xy. Find the equation of the tangent line at the points 3 and 3. By the way, does this curve passing through the 3 and 3? How do we know this? How we can check this? We simply substitute, right? X was the 3, y was the 3. It is going to be x cubed plus 3 cubed plus 3. What is the 3 cubed by 27. 27 plus 27 on the left, it is going to be 54. Then on the right, it is going to be 9 times the 6, which is also 54. Yes? The left side is equal to the right side. If you substitute x and y was 3, this curve is passing through this point. Okay? So let's find the equation of the tangent line. Do you remember how we find the equation of the tangent line? So any tangent line is going to have the equation y is equal to the kx plus b. And the step number 1 is you are going to find the equation, so the slope of the tangent line. And the slope of any tangent line is going to be y prime, okay? Sorry. The slope of any tangent line is going to be y prime at this point, okay? x0, y0. So in this case, it is going to be y prime at the points 3 and 3. It works always for any tangent line, okay? If this is half an hour, right? Okay, cool. Let's find a y prime. Can you help me to find a y prime? So in order to find a y prime, I need to find the derivative of all of the terms. Okay? So what is the derivative of the x cubed with respect to the x? 3x in a square. So you know how now, I think, how to take the derivative of the y cubed with respect to the y. If not, I'm going to I'm ready to, so you should write. Let's write this. dy cubed dx, right? is equal to the ty cube dy times to the dy over dx. It is going to be 3y cubed times the y prime. 3y squared, sorry. Okay? Then what is the derivative of the 6xy with respect to the x? So please note that y is some function of the x. We just don't know what it is. It can be sine of x. Y is equal to sine of x or cosine of x. Okay? We just denote it as the y. So let's say there's some ugly function. Y is equal to a huge function which depends only on x. I'm just denoting this as a y. Let's assume this. Okay? So we need to use something which is called a product term, right? The multiplication of the two functions which depends on y. This is what you wanted to say? Okay, good. Thank you. So you can help me. What is the derivative of the 6xy? 6y plus 6x y prime. Okay. So now I've got the derivative of all of the terms. It is going to be 3x in a square plus 3y in a square times y prime is equal to the 6y plus 6xy prime. I have to find a y prime from here. So that is why I'm going to put all of the terms with the y prime to one side, not with the y prime to another side. So it is going to be 3x in a square minus 6y is equal to the 6xy prime minus 3y squared y prime. And from here we can find a y prime. It is going to be 3x in a square minus 6y divided to the 6x minus 3y in a square. Okay? So the k is the slope of the tangent line is y prime at the points 3 and 3. I just need to substitute 3 and 3 in this equation. Okay? So you just need to validate 3x in a square minus 6y or 6x minus 3y in a square at this point 3 and 3. If you do this together, it is going to be 3 times to the 9 minus 6 times to the 3 divided to the 6 times to the 3 minus 3 times to the 9. I guess it's going to be negative value, right? So it is going to be 27 minus 18 divided to the 18 minus 27. It is going to be minus 1. Okay, so this is the slope of the tangent line. So now I've got y is equal to the minus x plus b as a tangent line. And I need to find a b. So since it is passing through 3 and 3, I know I can find a b, right? I'm just going to substitute this to here. So it is going to be 3 is equal to the minus 3 plus b. So that is why b is equal to 0? 6. Okay. So the y is equal to minus x plus 6 is the equation of the tangent line, which is passing through this curve at this point. Okay? So do you understand what is the implicit differentiation? Okay. Now let's do a super interesting example. So could you please tell me what is the derivative of the x in a square? Two x. What is the derivative of the 2 in the power of x? 2x times the ln of 2, right? Yeah? You need to always keep in mind that e in the power of x, okay? What is the derivative of, or let me write this with the y. What is the derivative of the x in the power of x? What do you mean say? Should I use x in the power of x as the power function? Or should I use x in the power of x as the exponential function? Which I need to use? Who thinks that I need to use this as an exponential function? Who thinks that I need to use this as a power function? Oh, come on. It is not neither power neither exponential. Yeah. Okay. Yes?
We should multiply to ln of e.
Yeah, okay. So if you multiply this to ln x, then it is going to be changed. The balance is going to be changed. Yes. You should then divide this as ln of x, and then it is going to be 6. Okay? Ln of e. Okay? We should multiply this to ln of e? Yeah. Okay. Okay? Yeah, I mean, you're right. We're going to take a ln from both of the parts. Okay? So because we want this x to go down, And the way how to do this, we're going to take ln of y and ln of all of these things here. Okay? Simply. Then on the left hand side, we're going to have ln of y. On the right hand side, you're going to have x times the ln of x. Right? So you see, so you build an equation where x and y are implicitly connected with each other. Okay, so you know definitely that y depends on x, but it is given implicitly. Now we're going to find the derivative of this thing implicitly. Okay, or before we do this, you need to know the derivative of the ln, which we haven't learned yet, but I'm going to simply provide this to you. The derivative of the ln of x is going to be equal to what? 1 over x. Okay, let's do this together then, quickly. So what is the derivative of the ln of y with respect to the x? It is going to be 1 over y times the y prime, right? It is equal to, now you have to use the multiplication rule, right? It is going to be ln of x plus x times the 1 over x, right? Then, so 1 over y prime is equal to the ln of x plus 1. So the y prime is equal to the y times the ln of x plus 1. Do you remember what was the y? It was x in the power of x times the ln of x plus, ln of x plus 1. So if y is equal to the x in the power of x, then y prime is going to be equal to the x in the power of x times the ln of x plus 1. Okay? So it is kind of interesting example where we need to use the implicit differentiation. Okay? So today we did some examples on the chain rule, implicit differentiation. For the next week, we're going to start super interesting topics, like the applications of the differentiation. We're going to learn a couple of algorithms which you have to implement later on. Okay? Cool, thank you. Bye.